Hi everybody, we have talked quite a bit about the ideal gas law, and today we're going to apply it in a lot of different ways. So, reminder, the ideal gas law looks something like this. PV equals N times a constant times T, right? And so we have pressure and volume and amount and temperature, and we have this constant R. So couldn't we solve that expression for R? Couldn't we set this equal to the constant? And if we wanted to solve for R, wouldn't that be PV with the NT divided out, right? And so we've done that before, and we actually plugged in those values at STP. We said 1 mole of any gas at STP equals 22.4 liters, and then we solved and we figured out the R value. But here's another interesting application. So let's call this our initial values. So this side of what I'm about to write, this is the initial side. And what I want to do is compare that to another instance in time where I solve PV equals nRT for R again, and we said R is equal to PV over NT. And I'm going to call this side my final side, right? And if they're both equal to R, then couldn't I kind of cancel out the R's here and say that PV over NT equals PV over NT? But remember, all the blue ones are initial, so maybe we want another way of writing that. Maybe we call these all P1. So P1, V1, N1, and T1, meaning initial. And on the right-hand side, these will all be 2. So P2, V2, N2, T2, those are all the final conditions. And so if I write the expression like that, something really interesting happens, right? So we are able to compare the initial and final conditions of pressure, volume, amount, and temperature. And just so you're aware, R actually does this for us. So we know that R is basically PV/NT plugged in at STP. So whenever we do an ideal gas law problem, we're simply comparing all 4 of these variables, PV, N, and T, to what they would look like at STP. So this is actually a really powerful gas law equation because it allows us to compare the pressure, the volume, the amount, and temperature of any gases under any conditions. But oftentimes, we're only going to compare 2 of those variables, right? So we can hold something constant. So imagine if we had N and T equal to one another on both sides of this equation. So N over here is equal to N over here, and T over here is equal to T over here. Well, if that's the case, we can essentially get rid of those 2 things, right, and just ignore them because they're being held constant. They're not changing, so they'd cancel out on both sides. So that means, look what's left. We have this expression, P1V1 equals P2V2. So we're going to start writing out expressions that happen when you hold stuff constant. So our first one, we said, was P1V1 equals P2V2. But couldn't I also hold pressure and temperature constant? Right? So imagine if you covered up pressure and temperature on both sides. You'd be left with volume over amount. So we could say that V1 over N1 equals V2 over N2. And couldn't we do the same thing with volume and amount? We could cover those up, and we'd be left with P1 over T1 equals P2 over T2. Or we could cover up pressure and amount, and we could be left with V1 over T1 equals V2 over T2. Or we could get really crazy and we could just cover up amount, and we could be left with P1 V1 over T1 equals P2 V2 over T2. And again, all of those are just coming from this derivation that we set up on the left-hand side, and what we're doing is we are changing which variables we're holding constant in each case. Now, if you have out your whole year resources page, I recommend having that. Here's the ideal gas law that we built all of those expressions from, and you'll notice that we have just derived all of those equations in the middle. What do they come from? Well, they come from keeping certain variables constant when you set PV equals nRT equal to R, and then set it initial and final conditions. So we're going to get some practice with those gas laws today. Your job is going to be to define variables from every problem. We have 8 problems to go through today. And in the interest of time, I have already defined the variables from the problems, so this video doesn't take an hour to go through. But if you want to pause and find these variables, feel free. So what I mean by that is looking at number 1, if you look at the question, you can see that V1, you're given an initial volume of 50 liters, you're given an initial temperature. I've already converted that to Kelvin because we know we need to use Kelvin for gas laws. We're given an initial pressure, yada, yada, yada. So if you look at this list of variables, you'll notice that you have initial pressure, volume, and temperature, and final pressure, volume, and temperature. So if I look at these 5 gas laws that I've written up here, you need to find one for question 1 that has pressure, volume, and temperature in it. The only one that fits that description is this one. And so that's the gas law that we're going to use. Now let's talk about what you'll earn credit for on assignments. So first off, whenever we do gas law problems, you're going to get points for making this list. You have to list out your variables from the question. This actually makes it a whole heck of a lot easier to solve. We're not just trying to be difficult by making you define that. It really sets the stage for what's to come. But you get credit for that. You also get credit for writing out the gas law that you're using. So we are using P1 V1 over T1 equals P2 V2 over T2. That is called the combined gas law. We don't need you to write down its name. I don't care that you write combined gas law, but you do need to write out the law. And then you need to solve it for the variable of interest. So we are looking for, in this question, V2. So we're going to show this being solved for V2. If I solve for V2, what will I get? Well, when I solve for V2, T2 gets multiplied up, so I'll have T2 times P1 V1 over T1 was over on the left-hand side, multiplied by P2 gets divided down, right? So that is the equation that we need to plug in. So you get credit for both of those steps, showing the initial gas law and rearranging. You also get credit for plugging in your values. So let's plug in everything that we have. We have our second temperature, our final temperature, which was 283.2 Kelvin. And remember, we're solving all of this for V2. So 283.2 Kelvin times that initial pressure, which was 1.08 atm, times our initial volume, which was 50.0 liters, over our initial temperature, which was 298.2 Kelvin, times that final pressure, which was 0.855 atm. So there's our equation, and there's some things we should look at. So first off, unit-wise, Kelvin on top, Kelvin on the bottom, gone. ATM on top, ATM on the bottom, gone. You'll notice the only unit that we have left uncovered is liters. That's good because we're searching for a volume. And sig fig-wise, another benefit of this list is figuring out your sig figs. So you have 3 sig figs here. You started with 3 here, you turned it into 4, but 3 is less than 4. 3 sig figs here, 4 sig figs here, 3 sig figs here. So because this is multiplication division, we care about number of sig figs. We go with the least number. We want 3 sig figs because all we have is 3s and 4s. So we have our final volume of 60.0 liters. All right, let's try another one. Define your variables, figure out which gas law to use, and then we're going to plug in and cancel our units. So when you define your variables for number 2, it should look something like this. You have initial pressure, volume, and temperature. So again, if you have P, V, and T all at play in a question, we need to use the combined gas law. So we again need to use P1 V1 over T1 equals P2 V2 over T2. In this case, we're solving for P2, so let's do that. When we solve this thing for P2, we'll still have P1 times V1 in the numerator, but now we need to multiply up that T2. And now we are putting it over T1 times V2 is now divided down to the denominator on that side. So let's plug in everything that we have. We know that we have an initial pressure of 1 atm. So we have 1 atm times our initial volume of 700.0 milliliters times our final temperature of 303.15 K over our initial temperature, which was 273.15 K, times that final volume, which was 200 milliliters. So before we cancel units, there's some things that people might have questions about. So number one is, when we started this list of variables, we know that we have gotten in the habit of defining or changing ml to liters. Why is that? Because R has units of liters times ATM over moles times Kelvin. And so the question is, why didn't we convert these milliliters to liters? The answer is, there's no R in these problems. In these initial and final condition problems, you don't have to worry about R because it's not an ideal gas law problem. We're not comparing to some R value, we're comparing to other conditions that are given. So if you look back at our list of variables, you'll notice that everything cancels even though we leave it in milliliters. So milliliters cancels with milliliters, Kelvin cancels with Kelvin, we're left with ATM, which is good because ultimately we are solving for a pressure, and so we want it in a pressure unit. Whenever we get to sig figs, when you solve this, you will get 3.884 ATM. This is 3.884 ATM because that's the unit that's uncancelled out. A lot of people want to say, well, wait a second, this only has one significant figure. What's going on there? Well, it turns out that, remember in the question, it says that we have a 700 milliliter gas sample at STP. So STP is a defined value, it's a definition. Therefore, the sig figs for STP, which is ST and P, do not count. So these two don't count in our sig fig list because they're definitions, and that's why we just have one ATM, and that's why we go the whole way out to the hundreds place with 273.15. So really, in terms of sig figs, the ones we care about are 700 point, which has 4 sig figs, 200 point, which has 4 sig figs, and then we have this 300 or 30.00 that has 4 sig figs. We turned it into 5 when we did the addition, but because we have 4s and 5s sig figs wise, that's why we end with 4 sig figs. Now the last issue is that we're not asked for ATMs, we're asked for what is the new pressure of the gas in PA. That doesn't mean in Pennsylvania, that means in pascals, right? So we need to do the math that we did earlier with pressure conversions to say that 1 ATM we know is equal to 1.01325 times 10 to the 5th power pascals. Whenever you do that, your ATMs cancel, you're left with pascals. This ultimately gives you, with 4 sig figs, 3.936 times 10 to the 5th power pascals as your final pressure. Just a little tip, if you would have rather converted this pressure, initial pressure, to pascals and then plugged into what I have in pink, plugged into the combined gas law, that would have worked just as well. Either way works. All right, moving right along to number 3. Our list of variables is a lot nicer in number 3, right? So we have a lot fewer variables. Based on our list of variables, we need an equation that has p's and v's in it. Well, if you come back up to your list of equations, p1v1 equals p2v2 has the variables that we need. So we're going to use p1v1 equals p2v2. Notice that in the question, we are asked to solve for v2. So let's solve for v2. v2 is going to be equal to p1v1 over p2. We're going to plug in everything that we have, so that initial pressure is equal to 947 ATM times that initial volume was 150 milliliters, 150.0 milliliters actually, over our second pressure, which is 0.987 ATM, and this is so we can solve for V2. You'll notice that your ATMs cancel, you're left with milliliters. Sig fig wise, on our list of sig figs we have 4, 3, and 3, so our answer here should have 3, and we end up getting our V2 as 144 milliliters. you'll notice in the question that all we are asked for is what will the volume be? And it doesn't tell us what units of volume. So if it's any units of volume, we've ended with a unit of volume, milliliters. We don't need to do anything else. You could obviously convert that to liters if you wanted to, but the question doesn't ask you to, so we're not going to. There's no real reason to do that. All right, let's try number 4. Again, in number 4, we have a list of variables, and this one is P1V1 and P2V2, right? So we're again going to be using Boyle's law. P1V1 equals P2V2. In this case, we're asked to solve for P2. So if we want P2, we're going to have to divide out V2. So P1V1 over V2. Let's plug in everything that we have. We have 608 mmHg as our initial pressure. We have an initial volume of 545 cubic centimeters. And we have a final volume of 1,065 centimeters, cubic centimeters. And again, we're looking for, in this case, our second pressure. So when you do the math here, your cubic centimeters cancel. You have 3 sig figs, 3 sig figs, and 4 sig figs, so we should end with 3 sig figs. Our final pressure turns out to be 311, and the unit is mmHg because that is still remaining from our math. Another thing that we should talk about that's worth just thinking about is, does this make sense? Right, so we're looking at what happens pressure-wise when we change a volume. You'll notice that our volume got bigger, right? We started out with 545 cubic centimeters, that was our V1. We let that grow to over 1,000 cubic centimeters. So if you have the volume grow from 545 to 1,000 cubic centimeters, it makes sense that the pressure releases just a bit, right? There's not as much pressure if you give it a much larger volume to occupy, and that's what we see, right? Our pressure has decreased from 608 all the way down to 311 because there's a lot less pressure on this gas. All right, looking at the variable list in number 5, we have volume and temperature, initial and final. So we need an equation that includes volume and temperature, which is V1 over T1. So we'll be using V1 over T1 equals V2 over T2. You'll notice that we're looking to find V2. So if we're looking to find V2, we need to multiply up T2. So we will end up with V1 times T2 over T1. We can plug in everything that we have. So that initial volume is 752 milliliters. That final temperature was 323.2 Kelvin. And we're putting that all over that initial temperature, which was 298.2 Kelvin. Your units will cancel here. Kelvin's gone. We're left with milliliters. You have 3 sig figs, 4 sig figs, and 4 sig figs, so we'll go with 3 sig figs. Our final volume turns out to be 815 milliliters. And again, you can ask yourself, does that make sense? If we have a gas and we increase its temperature from 298 to 323, does it make sense that it occupies a larger volume? Yes, it does, because those molecules are moving faster, they're bouncing off the walls a little bit with increased energy collisions. That means that the volume occupied gets a little bit larger. So this again makes sense logically. Let's look at our list of variables for number 6. So number 6, we again have temperature and volume, and temperature and volume. So we again are going to need to use V1 over T1 equals V2 over T2. Now when we do this, you'll notice that we have to solve for T2. So things are a little bit messy when we solve for T2. You have some options. Option number 1, you know that T2 currently is in the denominator, right? It's downstairs. So we need to multiply it up to the numerator. Some people do this, don't do this, right? Some people say, oh, I want T2, I'll just divide out V2 on both sides. I'll do V1 over T1 V2 equals T2, right? That's not true. That's equal to 1 over T2. So that's definitely not what we want. We know initially we need to get T2 into the numerator. So let's get T2 into the numerator. How do we do that? We multiply T2 up to the left-hand side. So we'll get T2 V1 over T1 equals V2. And then we need to clear out everything except for T2. So we need to multiply by T1, we need to divide by V1. So ultimately, we will get that T2 is equal to V2 times T1 over V1. And then we'll plug everything in, right? So if we want to plug in, we know that our initial volume is 500.0 milliliters. We know that our initial temperature is 273.2 Kelvin. And we know that our final temperature, excuse me, not our final temperature, our initial volume, pardon me, our initial volume is 375 milliliters. When you do that, milliliters will cancel. You have 4 sig figs, 4 sig figs, and 3 sig figs. So we'll end with 3 sig figs. Our final temperature will be 364 Kelvin. And that's all well and good, except we are asked what Celsius temperature. And so we need to, at this stage of the game, come back and do some subtraction. 364 minus 273.15 gets us to Celsius, and that gives you 91 degrees Celsius as your final temperature. And you'll notice we could not just do this problem in Celsius. And this one's a good example because you started with 0 degrees Celsius. So if you plug a 0 in anywhere here, you would just figure out that, hey, the whole thing's 0 all across the board. Nothing changes. So we can't just use 0. We can't use Celsius. That's why we have to use Kelvin for gas laws, because we take 0 out of the equation. All right, let's try 7. So 7, again, has a list of variables. In this case, we have pressure and temperature. So looking up at your list of equations, which one has pressure and temperature? Well, it's P1 over T1. So let's dive in with P1 over T1. And that, of course, is equal to P2 over T2. We are interested in solving for P2. So let's do that. When we solve for P2, we are going to need to multiply up T2. So P2 will be equal to P1 times T2 over T1. We're going to plug in everything that we have, right? So that initial pressure is 3.00 atm. We're multiplying times our final temperature, which is 325 Kelvin. And then we're putting it over our initial temperature, which is 298 Kelvin. And again, this allows us to solve for P2. So when we do that, our units will cancel conveniently. Kelvin and Kelvin cancel. We're left with atm, which is a pressure, so that's good news. 3 sig figs for every single number, so our answer should have 3 sig figs. We get 3.27 atm. All right, last one. We're doing great. Let's define our variables for number 8. So there's our list of variables. You'll notice in this case, we are solving for T2. We have pressure and temperature again. So again, we're going to use P1 over T1 equals P2 over T2. And much like what we saw in number 6, again, we need to solve for something that's down in the numerator, or excuse me, down in the denominator. It's down on the bottom. So here's another method for solving for something in the denominator. You may cross multiply if you so desire. This might make things look a little bit cleaner. So let's multiply T2 to the left-hand side. Make that T2 P1. Let's multiply T1 to the right-hand side. Make that P2 T1. We ultimately want to solve for T2, so now all that's left to do is divide by P1. So ultimately T2 is going to be equal to P2 T1 over P1. Right, and that's kind of what we see whenever we cross multiply and take it out. So either way works, what we did in number 6 or what we did there. Regardless, in order to solve for T2, you need to plug everything in. So your final pressure is 2.00 atm. Your initial temperature was 295 Kelvin. Your initial pressure was 1.20 atm. your ATMs will cancel. We're left with a Kelvin temperature. Notice 3 sig figs, 3 sig figs, 3 sig figs. So our T2 will end up being 492 Kelvin. But again, if you look back to the question, this one asks us for a Celsius temperature, so we again need to subtract off 273.15, and when we do that, we will get a final answer of 219 degrees Celsius for our final temperature. So in summary, obviously we did a lot of work on this video, but all we're really doing is letting the problem lead us to a list of variables. You get credit for that. Once we have a list of variables, we are using the list of variables to pick one of those gas laws. Remember, you're given those gas laws on a test. You just need to be able to figure out which one applies. Once you figure out which gas law you're using, you get credit for writing that gas law down. You get credit for rearranging the gas law for the appropriate variable. You get credit for plugging in the numbers with units. You don't have to physically cross out the units like I've been doing, but it can be helpful. We just want to show you or allow you to show us that your units would cancel out because one's in the top, one's in the bottom. And then you need to solve with correct sig figs with the correct value and with a unit as well at the end of the day.